We're going to perform an experiment to illustrate the wave nature of light, and we will also be able to measure the wavelength of our light source. This experiment is similar to one that Thomas Young performed in 1801 to illustrate the wave nature of light. This experiment is often referred to as Young's double slit experiment because it involves a monochromatic source of light impinging on two slits. So let's imagine this plane wave propagating towards the two slits, and it helps to just think about what would happen if this was a water wave. And from each of these little slits, what will happen then is it will be a source of a spherical wave that's propagating. And as these two spherical waves propagate, they're going to overlap and start interacting. So now what we want to do is go to a plane that's some distance away from our double slits and look at the pattern that's going to occur on that plane. Now let's go back to thinking in terms of our light waves. And if we're looking at the region on our screen here, midway between the two slits, we see that the spherical wave emanating from the top and bottom slits will have traveled the same distance, same number of, say, wavelengths, and so there will be constructive interference and you'll get a bright fringe here. Now, if you move up, you'll reach a point here where the path lengths from the two slits will be a half a wavelength different. You will have destructive interference and a dark spot. And if you move up here, we'll get to the first order fringe where the path length from the top slit and the bottom slit differ by one wavelength. So in other words, if we take a line that goes from the top slit and is perpendicular to the line of sight from the bottom slit to the first order fringe, this distance right here will be one wavelength. Then if we move up, we'll get to a dark spot and then another light spot, which will be our second order fringe. And so now the difference in the two path lengths is two wavelengths. In the experiment, we will be illustrating the spacing between our slits is going to be less than a millimeter, and we'll call that spacing D, and the distance to our screen is going to be several meters, and we're going to call that distance L. And the distance from the 0 order to nth order interference fringe we're going to call Y. Okay, so let's look at this right triangle here where the hypotenuse is the spacing between the slits. And this length here is the path difference, n lambda, or 2 lambda for this specific case. We're going to call this angle theta here. So the sine of theta is going to be 2 lambda over our hypotenuse d, or n lambda over d. Now, if we look at this right triangle, where the hypotenuse is the distance from the midpoint of the slit to the interference fringe we're looking at, we see that that hypotenuse is perpendicular to this line, and from the center of the slit to the 0 order interference fringe is perpendicular to the hypotenuse of our original triangle. So this angle here is also theta. Now the tangent of theta is going to be y over L. Now, since the spacing in our slits is less than a millimeter and our distance to the screen is going to be several meters, theta is going to be small. When theta is small, the sine of theta is approximately equal to the tangent of theta. So 2 lambda over d is going to equal y over L. And if we were looking at the nth interference fringe instead of the second, this 2 would just be an n. So the equation that we come up with then is that n lambda over d is equal to y over L. So this will allow us to measure the wavelength of the light we're looking at, because from the dimensions of our experiment, we will know L, we will know the slit spacing D, and then we will measure Y based on the interference fringes that we observe. And from that, then, we'll be able to measure the wavelength of our light, lambda. I'm going to use this green laser pointer as our light source, and we're going to do the experiment the way Thomas Young did it. He did not use two slits. He used a narrow barrier, and we are going to use a thin wire that's 0.195 millimeters in thickness, which I'm going to slide across the aperture of the laser. And now you can actually see the interference pattern to the left and to the right. The laser is too close to the paper to clearly make out the light and dark fringes, but we'll be setting up the experiment in just a minute with the laser much further away from our screen, and then we'll clearly see the light and dark fringes. So the wave function associated with each photon in our light beam will be separated into two parts by this thin wire, and then those two parts of our wave function will interfere and form our light and dark fringes on our screen. We have the laser pointer mounted on this desk at the back of the classroom. We're 9 meters from the chalkboard where we will be projecting the interference pattern. And there the laser is turned on. Let me turn off the lights. And there's our interference pattern, and now let's go closer to the board so we can get a better view of it. Okay, so here we can clearly see the interference pattern using the green laser. We see the bright central fringe. So let's go 1, 2, 3, 4, 5, 6. So out to 6 fringes here. So we're going to measure here the distance from the n equal 0 to the n equals 6 fringe. So here's the mark I made for the n equals 0 and n equals 6 interference fringes. And that spacing is about 13.8 centimeters. We can now get a determination of the wavelength of our laser light from our measurements. So the distance we measured from the n equals 0 to n equals 6 fringe was 13.8 centimeters. And so n is 6. The distance from our laser to the chalkboard we measured with a tape measure and obtained about 9 meters. And the thickness of the wire we were using across the aperture of our laser was 0.195 millimeters. So that gives us a wavelength of 498 nanometers. Now the actual wavelength of the laser I was using I know is 532 nanometers, so we have about 6% error. But that's not too surprising because of our crude measurement of the distance from our laser to the chalkboard, and also the crude measurement on the chalkboard of the spacing between the n equals 0 and n equals 6 fringe.